All right, let's jump right into this explainer. Today, we're exploring how modern cities are transforming themselves from having massive, sprawling pollution problems into cutting-edge zero-waste hubs. You know, when we think of smart cities, we almost always picture glowing lights and self-driving cars, right? But today, we're actually digging into the gritty, essential reality of how these cities are going to handle the millions of tons of waste we generate every single day. We've got some fascinating ground to cover today. We'll start off with understanding environmental pollution, move into the zero waste blueprint, and then tackle segregation, the sorting challenge. From there, we'll dive into AI-powered waste classification, low-cost urban composting, and wrap up with building a circular economy. Basically, we're starting at the root of pollution and ending with how deep learning and microbiology are quite literally saving our smart cities. Okay, Section 1, Understanding Environmental Pollution. To fix our urban waste crisis, we first have to clearly define what we are actually fighting against. The EPA identifies two main categories of pollution that agencies are desperately trying to manage. The first is point source pollution. This one is highly confined. You can literally point a finger right at the culprit. We're talking about highly toxic heavy metals, sulfur dioxide, or nitrogen dioxide just spewing from a specific factory smokestack. It also includes that nutrient-heavy, chemical-laden wastewater discharged directly into rivers from places like paper mills, auto plants, or oil refineries. Because we know exactly where it's coming from, regulatory agencies can actually monitor and regulate those specific sites. But then we have non-point source pollution, and the contrast here is absolutely crucial. While point source is confined and trackable, non-point source is this sprawling, collective mess. It's pollution that enters the environment from many different places all at once. Think about it. When it rains, water washes over city streets and agricultural fields, and it picks up this massive toxic cocktail: synthetic fertilizers, microplastics, motor oil, untreated biological waste, and drags it all straight into our ecosystems. And you know, our growing municipal solid waste crisis operates a lot like this non-point source problem. Millions of households generating all kinds of waste every single day. The old model of just collecting all that scattered waste and burying it in a landfill, it's completely failing us and placing a huge strain on our environment. Which brings us to Section 2, the Zero Waste Blueprint. Because those traditional collect and dump models are failing, we have to shift to a framework that prevents waste in the first place and recovers its value. Let's break down how this zero waste system actually works in practice, stepping from simple source reduction all the way to recovering energy. Step 1 is auditing, figuring out exactly what is in our waste stream. Step 2 is source prevention. That means shifting to digital processes, ditching single-use plastics, buying in bulk, things like that. Step 3 is aggressive composting and recycling. And Step 4 is recovering value from whatever is left over, like processing non-recyclable waste into refuse-derived fuel, which industries can use to cut down on fossil fuels. This quote brilliantly illustrates the main hurdle we face here. Think of recycling like cooking. If your ingredients are all mixed up, the final result will fail. That really hits the nail on the head. Separation is the ultimate bottleneck. If organic food waste gets mixed in with recyclable paper or plastic, the whole batch gets contaminated. It's worthless. Proper segregation right at the source is the absolute foundation of a circular economy. Moving right along to Section 3, Segregation, the sorting challenge. Now, sorting this mountain of waste by hand is incredibly slow, expensive, and super prone to contamination. Honestly, human hands just can't keep up with the exponential growth of our trash. That is exactly why researchers are turning to computer vision. Using datasets of over 25,000 images sourced from Kaggle, scientists are teaching machines how to tell the difference between organic materials and recyclables. To standardize everything, they convert the images to RGB, apply edge detection, and resize them to exactly 150 by 150 pixels. They even flip and shift the images during training. That way, the AI learns to recognize a crumpled Dr. Pepper can or a half-eaten apple from literally any angle, which makes the model way more robust out in the real world. And that brings us to Section 4, AI-powered waste classification. This sorting challenge sparks a massive technological leap, using deep convolutional neural networks, or CNNs, to totally automate the process. What we're looking at here is a complex network of dense blocks and transition layers called DenseNet 121. It's a transfer learning model. This means researchers take an AI that already knows how to recognize shapes and patterns in other areas, like medical imaging, for example, and they fine-tune it specifically for waste. Within this architecture, notice how each layer inside those dense blocks receives inputs from all the previous layers. It's a brilliant design. It boosts efficiency, promotes future reuse, and proved to be incredibly robust at identifying waste types, far outperforming custom-built networks. The results of this are just staggering. When tested against older machine learning models like random forest or support vector machines, which usually hover around 70 to 72% accuracy, the deep learning DenseNet 121 model hit a 91% accuracy. It also scored a 0.98 ROC AUC, which is just a technical way of saying it's incredibly reliable at telling organics and recyclables apart. Researchers even tried tweaking the older models with a dimensionality reduction technique called PCA, but the benefit was totally negligible. The data is super clear. Deep transfer learning is absolutely the future of automated waste sorting. Let's look at Section 5, low-cost urban composting. Once the AI successfully separates out that organic waste, we need an efficient way to process it in tight urban environments. Remember, in a lot of cities, organic matter is nearly half of all municipal waste. Traditional windrow composting is great for big operations, but it requires massive land buffers for greenhouse gases, and it takes up to 90 days. Vermicomposting, using worms, produces awesome fertilizer, but it needs strict temperature controls and also takes nearly 2 months. Enter the Takakura method. It is a compact, low-cost miracle designed specifically for dense, smart cities. Just 10 to 14 days. That is how fast the Takakura method can break down organic waste. In less than 2 weeks, it slashes the waste volume by 40 to 50%. If you implement that on a citywide scale, this rapid decomposition can cut emissions by up to 132 tons of CO2 equivalent every single day. It fits perfectly into space-constrained households and can easily be paired with larger, centralized facilities to maximize urban waste diversion. Finally, Section 6, building a circular economy. Now we have to connect all these micro-innovations into a macro solution for our cities. By feeding this real-time AI classification data into a data-driven decision support system, or DSS, city planners unlock some serious capabilities. As the data flows up to the cloud, municipalities can dynamically optimize their waste collection routes. They can track exactly how much organic waste is heading to those Takakura composting centers and make sure pristine recyclables head straight to material recovery facilities. It's a total game changer that minimizes our reliance on environmentally destructive landfills. So, I'll leave you with this question. How might your city implement hybrid AI sorting and rapid Takakura composting to eradicate waste and close the circular economy loop? It's really something to think about, because the blueprint for a zero-waste future isn't some far-off pipe dream. It's literally already here, in the data, in the AI models, and in a microbiology of rapid composting. We just have to put the pieces together. Thanks for joining me on this explainer, and definitely keep looking for ways to close the loop in your own community.